Hey everyone! We're doing chapter 9.3 all the way to 9.5 today, where we're going to be covering annuities, payout annuities, and loans, which are all related. So keep that in mind, and let's get started. First up, we've got chapter 9.3, which is annuities. So what is an annuity? Well, in the previous bit, we actually addressed the idea of putting a large chunk of money into an investment and then just waiting some time. That's not a great idea if you don't happen to have large chunks of money lying around. Most people don't. So instead, what happens is you save up a little bit every month or every week or every 2 months or whatever, and you just add that to an account on a regular basis. And that is an annuity. The best part about this is that by adding money to the account directly, this means that you're going to get even more interest every month or every day or every week or whatever. Uh, and by the way, this also implies that we're working with compound interest. You can't add money to something like a simple interest situation. It doesn't really mean anything. So how much are these things even worth? Well, like the previous sections, I have given a formula. Looks like this. It's kind of messy. I'm sorry. The ones in chapter 9.4 and 9.5 are worse, not much worse, but still worse. But in any of the cases, please don't try to memorize any of these. That just will be overly stressful. The reason that the PDF exists on Canvas that you can see of all the formulas is so you can use that for the quiz and the test and whatnot. Makes your life a whole lot easier. In this case, A doesn't actually stand for annuity. I know it seems like a thing it should do, but it actually stands for accrued amount. That's the total amount. M is the regular payment. It's usually monthly. I think that's why it's an M, but I'm not sure. R is the APR, or the annual rate. N is the number of times you compound a year. T is the number of years. And yes, that is N times T in the exponent. That wasn't a mistake. So I will mention this is that sometimes you'll see in a problem they don't mention the number of times something is compounded. Unless you are explicitly told otherwise, we can assume that this is the exact same as the number of times that money is added in that given year. We assume that they happen at the same time and all that stuff. If you don't assume that, then the formulas get way more complicated. So unless you're explicitly told otherwise, we just assume that. That means that if you pay once a month, you compound interest once a month. And for ease of effort, I personally recommend solving for r over n and then just using that in the equation. Don't do this like when you see it. Do it at the beginning. It'll make your life a little easier. Just a recommendation, not a requirement. Let's do a problem. So let's say that Ollie decides to invest 500 bucks every month into a retirement account with a 3% APR. He's going to retire in 40 years. That's the hope anyway. And the basic question is, how much is he going to have in the end? Well, we've got this formula, so let's use it. And by the way, once again, since I didn't specify that he's compounding every month, but I didn't specify that he was compounding in any other quantity, we can assume it's once a month. We can assume that it's whatever the payment rate is. So plugging in the numbers, you'll see 500 for M, because that's the monthly payment. 0.03 is our R, because that's our rate. We compound once a month, so that's 12 times a year. We do it for 40 years, so we have a 12 times 40 in the exponent. The 12 is also because it's 12 times a year. And then minus 1. That's just part of the formula. I simplify it. I'm not going to talk through it step by step, by the way, but I do try to simplify each one of these step by step. So if you have a hard time with any of this, you can look at the PowerPoints, and I have tried to make it visible so that it's easy. And we have $463,029.75, which is a sizable amount of money for retirement. I don't know how comfortable Ollie wants to be during his retirement age, or how long he plans to be retired, but that's a decent chunk of money. Let's give a different example. Ollie, he tries to be clever. He wants to retire earlier, so he's only going to save for 20 years, but he's going to do 1,000 every month. He's got the same 3% APR, don't worry. So if he does this, well, you plug in the same values, you can simplify, and you get $328,302. But, well, that's considerably less than the 40-year version, even though he's technically contributing the same amount of money. If he pays $1,000 for 240 months, and I say 240 because it's 12 times 20, instead of 500 for 480 months, because that's 40 times 12, or 12 times 40, whatever way you like better. He makes less money in this version because the time for the interest to kind of collect is less, so it doesn't build up nearly as much, and he's much better with the 40-year plan, even if that means that he has to retire in 40 years instead of 20. If he'd like to save more money, he's going to get more, but it's, time is always the best factor here. We'll give a different example. Hannah, she's going to save for a home. She's going to save for 10 years. She wants to have $300,000. That's her goal. She'll just buy the home outright. It'll be a cheap home, but it'll be a home. And the interest that she has in her account is 5%. She's going to add to this annuity every single month. How much does she need to add in order to do so? And more importantly, how much of that money that she will have saved in the end was directly added by her as opposed to being added by the interest? Like, the interest is going to add something, but how much of it is just her? And in the previous sections, we can plug in the values we already know and solve for the values we don't. That's true for the first bit. It's not true for the second bit. Well, sort of. But we'll get to that in a second. There's our formula. Again, don't memorize it. When I plug in the values, now the value that we haven't plugged in is our M, because we don't know how much money she's going to have to pay every month. And we do know how much money she wants to have in the end, so the $300,000 is on the left side because that's our accrued amount. She's got 5%, 12 times a year, 10 years. We plug in the formula, it cleans up, and we get to this point where we have $300,000 equals M times 155.282794. You'll notice that I've been rounding well past the cent mark, and that's because there's a problem in real life called rounding error, where if you round when you start doing like multiplication or division, you can easily make the error get bigger by just those processes. So if you only round to the nearest cent for everything, then you're going to be wrong by potentially several cents or even several dollars, depending on how big the numbers are. So always round well past the cent mark. In this case, I did way more than necessary, but if you can't save it into your calculator directly, just always go excessive. And then afterward, we can divide out the 155.282794 on both sides, leaving us with M on the right side. And we get M is about $1,900. It's $1,931.97, which is Hannah's monthly payment. I didn't just ask Hannah's monthly payment though. I also asked what the amount she added to the account. And to do that, we just say how many months did she pay times how much did she pay a month. It's not a particularly complicated process. You plug that into a calculator, get $231,835.85. So that's how much she contributed, but she got $300,000, so pretty good. That's 70, almost 70 grand that she didn't have to pay. Jumping into our next topic, we have payout annuities. What's a payout annuity? Well, it's the opposite of an annuity. Specifically, in the case of an annuity, we add regular payments we save up every month so that we can take out the amount at the end, so we can have that $300,000 or whatever. Instead, we're doing the exact opposite, where imagine if you do save for retirement, your goal is to withdraw regular payments so that you can pay all of the bills you still have as a person without, going to work. And you plan to do this for several years. That's the whole point anyway. And this is a payout annuity. It works like the same thing, but in reverse. And you could technically take out all the money in your account once you have that fabled large amount of money in your account. But if you leave some of it in, as you only need to withdraw it when you need it, then the money you leave in will collect interest, and that's good for you. So let's calculate a payout annuity. We've got another formula. Again, don't memorize this. I've color-coded it this time, though. And our formula is P equals M times 1 minus 1 plus R over N, all to the power of negative N times T, all over R over N. P is our principal or starting amount. M, just like before, is our regular withdrawal amount. R is our percentage rate. N is the number of times we compound. And again, unless specified otherwise, we're going to assume that that's the number of times that you're withdrawing as well. And T is just the number of years. By the way, once again, that exponent is a negative number. That is allowed. We're not going to go into what that means. It's not super complicated, but it is there. And make sure when you're putting into your calculators that you don't forget the negative exponent. Let's give an example. Jose, his goal, he wants to withdraw $30,000 every year for the next 10 years. His account offers 7% APR. How much does he actually need to put into the account in order to pull off such a feat? Well, just put in the values we know and solve for the ones we don't. In this case, 30,000 is our regular payment. I know that M seems like it should stand for monthly, but it's actually our yearly payment. So Jose gets 30 grand every year, so that's what he's putting there. His interest rate is 7%. He's doing it once a year. That's also the number of times he's compounding a year because, again, if you don't specify, then you're doing the exact same as the withdrawal rate. And it's doing it for 10 years, so there's a 10 there. You can simplify and get to $110,000 along with $707.45. Don't forget the little bits too. This thing means that he technically made 90 grand over the course of this 10 years, even while he was taking money out of his account. That 90 grand, meaning he would have gotten $300,000 if he just wanted 30,000 times 10, but by putting it into an account, he actually made the money on the interest because he wasn't collecting on the future payments. Like he didn't have them already. We'll do one more example and then on to loans. Chris has already saved $500,000 for retirement. Put it into account. Chris wants to withdraw monthly for 15 years, and the account has a 5.4% interest rate. How much is every withdrawal going to be? We are assuming that Chris is going to take the maximum amount without going broke until the very end. So we have 500,000 equals M. We don't know what M is because that's our monthly payment, and we don't know. Times 1 minus 1 plus 0.054 over 12 to the power of negative 12 times 15. 0.054 is our rate. 12 is the number of times we compound. And 15 is the number of years. And don't forget to divide by 0.054 divided by 12. Either way, when we simplify that whole bunch of numbers, we get $500,000 equals M times 0.55433,287 divided by 0.0045. And that simplifies to M times 123.18508,204. But notice we have to solve for M, so we still haven't finished yet. We divide both sides by that 123 number, and we get $4,058.93. This means that because Chris has saved $500,000 for retirement, Chris gets to withdraw $4,058.93 every single month. So that's kind of nice. And you get to do it for 15 years. So let's talk about loans. Now, when we talk about loans, what we're really talking about often is when a loan is paid off over time, like you pay multiple times, which basically means that you get a large sum of money, but then you just make regular payments. And the unpaid stuff, the stuff that you have yet to pay and will pay in the future, hopefully, that collects interest. But unlike the interest in the previous examples, this interest we can almost think of as bad because it, means you have to pay more money. This situation is the exact same as the payout annuity. It doesn't sound like it, but I promise it is, except the roles are reversed. What do I mean by that? Well, since in the case of a loan, let's say you take a loan from the bank, that means that the bank pays you a lump sum, and then you pay back regular payments. Well, in the case of a payout annuity, you make the regular payments to take out a loan. Well, that's the exact same thing, but now you're spending money when the bank is getting the money. So a loan is basically a payout annuity for the bank, or really whoever is offering the loan. There's our formula. Notice it hasn't actually changed because it is literally the exact same thing. It's just one of them is kind of unfortunate for you because you now owe money, and one of them sounds great because you get money paid to you on a regular basis. Let's give a fun example. Seth wants to buy a new phone. Seth doesn't have a bunch of money lying around, but he has budgeted 30 bucks a month, right? He can do this. And there are loans that you can have on phones. And in this case, there's one for 1 year at 6% APR. He wants to take out the biggest loan he possibly can so that he can get the coolest phone possible. What is the biggest loan? Plug in the relevant terms, and you get all of that. See that 30 is his monthly payment, and 0.06 is his rate. 12 is the number of times he's compounding. T, R1, well, that's because we do it for 1 year. And, when we clean all of this up, we get $348.57. So he's probably not buying the brand new iPhone, which probably costs like $1,000, but he's not getting nothing. So that's kind of nice. Give a different example. Wallace is going to borrow $5,000 at 12% APR, which does not sound fun. The question is, how much does he have to pay every month, assuming that the loan is only about 6 months? By about, I mean it's exactly 6 months. So when we use our formula, we get 5,000 equals M. Once again, we don't know what the monthly payment is, so we have to figure it out. And, well, we put in our 12% interest rate. We divide by 12, which, well, fun fact, 12% divided by 12 is 1%, so it cleans up nicer than the previous problems. But regardless, notice that the years is now in 0.5 because we're only doing this for half a year. T is measured in years unless you change all of the values to reflect it. So like the percentage rate and stuff like that has to change too, and that's a pain in the neck. We simplify the problem even more, and we get 5,000 equals m times 5.795476, which is nice. And when we clean that up, we get $862.74. So, not a great monthly payment, but hey, $5,000 right now. Now, one thing you can do with a loan is pay off a loan, like pay it early. So oftentimes when you get a bill for something like a credit card bill or a phone bill or whatever, there's often an option to pay more money than you need to, with the idea that if you do so, you'll pay it faster, which is kind of nice. If you pay off everything, the benefit is that you don't actually have money that you still owe, which can collect interest over time. So if you realize that, hey, I can now afford to pay off the loan early, then you won't owe more money in the future because it will have been paid off. The price remaining can be solved by finding out how much would happen if you had a shorter loan for the amount of money with the same kind of monthly payment. I'll explain. I promise. It's a little weird. So we'll have one more example and then we'll be done. This is a tricky one though, so be aware. Bill takes out a loan of $800,000. It's going to be at 2.8%. It's compounded quarterly for 20 years. Directly after making the 17th payment, he decides he's going to pay off the loan, like the moment afterwards, so we're not worried about interest accruing over the time between him making the last payment. How much would that cost, assuming that he's allowed to? To find out, step one, all we have to do is find out how much he was paying every single quarter, because it's compounded quarterly. In this case, by using our formula, I cleaned it up really quickly. You can check my work if you want, but I got m times 61.09649658 equals 800,000, or when you divide both sides so that m is on one side by itself, you get m is $13,094.04. So in this example, he's paying 4 times a year for 20 years. That's 80 payments. But Bill already made 17 payments, so we've got 63 to go. So how much money does he have to pay if he just pays right now? Well, technically, if you kind of think about it, what this would be is that this is sort of a loan, but in reverse, in that he is basically paying them the amount of money he would get at the same exact interest rate, but with 63 payments. And specifically the principal of the loan, since he's giving the lump sum this time. So look at the interest payments for a 63 payment loan. And in order to do that, you could try to solve for what the amount of time you have left, but honestly, you don't have to, because the exponent, which is where the time is located, is always n times t, and n times t is just the number of payments. So if we know the number of payments, we don't even need to calculate what t is. You can, there's nothing wrong. It would be 63 over 4, which is not a super nice number, but you can do it. Either way, you get $665,211 and, of course, 5 cents. Since he's paying early, he just has to pay that. He just has to pay the principal in order to pay the unpaid balance, he's just paying $665,211.05. He would pay more than that in total if he had not done that, by the way. So that's it. Make sure to do the homework and the quiz. They're all due Sunday at midnight. The test is available on the very next day. The second after the homework and quiz is due, the test is available, and that'll be available once again for 24 hours. If you have questions, email me, message me. Uh, come to my office hours. Those are my office hours. That's pretty much it. That's the whole section. There's plenty more you can do by talking about finances, but we're just going to end it there. If you have any questions about financial math in any capacity that isn't covered by this, I'll also be happy to answer those as well. But I'm not an expert in that space or remotely savvy when it comes to what to actually invest in, but I can help kind of give you some information. That's it. Have a great day.